Hello everyone, I am PhCz and today I'll present my work on reliable prediction of singlet-triplet gap in TDDF molecules with two distinct theoretical methods, namely the time-dependent density functional theory and the GW-BSE approach. Today we are going to discuss the following. Firstly, I'll give a brief introduction about the OLED molecules. Secondly, I'll talk about the mechanism and the factors that affect the thermally activated delayed fluorescence in such molecules. Thirdly, I'll talk about the theoretical methods and the results. And lastly, I'll conclude the talk with some important conclusions. In this slide, we are going to discuss the evolution of the OLED molecules. In panel A, we discuss the first generation fluorescent emitter molecules. As per spin statistics, 75% of the excitons generated are the non-emissive triplets, whereas the 25% are the emissive singlets. This is shown by the S1 and T1 in the figure. However, these OLEDs have a low internal quantum efficiency of 25% only. To overcome this problem and to harvest the triplet excitons, the second generation emitters were designed, and this is shown in panel B. These were phosphorescent emitters and included heavy atoms such as iridium. Due to the high spin orbit coupling, the phosphorescence from the triplet states were possible. However, these OLEDs were highly toxic in nature and also expensive to produce. Lastly, a special class of OLEDs were designed where the triplets can be upconverted to the emissive singlet states through the reverse intersystem crossing mechanism. Note, for efficient reverse intersystem crossing, the singlet-triplet gap has to be small, in between 0.1 electron volts to 0.5 electron volts, and must contain specific donor and acceptor groups. These were efficient, cheap, and non-toxic in nature, and thus are preferred as emitter molecules. Now let's discuss the mechanism and the factors influencing the thermally activated delayed fluorescence. For this, let's focus on figure 1 on the left side of the slide. It was established by Adachi and co-workers that efficient emitter molecules must contain small singlet triplet gap, which can be achieved if the HOMO and LUMO are localized on different fragments of the molecule, and also they must contain a twisted donor acceptor structure. If the electrons and holes are localized on the same fragment, then we classify them as a local excited state, and if they are localized on different fragments, then we identify them as a charge transfer state. In this respect, we show three molecules in figure 2 with low and high singlet triplet gap. PhCz and NPH3 are used as transport layers in OLEDs and have a high singlet triplet gap in comparison to the 2CZPN molecule, which is basically an emitter molecule with a singlet triplet gap between 0.1 and 0.5 electron volts. Now we discuss the theoretical methods we use to calculate the excited state energies. First, we discuss the time-dependent density functional theory. The TDDFT is an inexpensive method with a reasonable compromise between the accuracy and the computational cost. However, one must keep in mind that pure functionals underestimate charge transfer excited state energies due to the omission of Coulombic electron and hole attraction. However, to bypass the issue, we can use hybrid functionals with uniformly weighted electron hole attraction, such as MO6-2X, and optically tuned range-separated hybrid functional, such as LC omega PBE, where omega is optically tuned. The amount of exchange included in the Hartree fork for these functionals is shown in figure 1 on the right. For the range-separated functionals marked by the dashed red circle, we see that they switch from DFT to exchange at large interatomic distances. Next, we discuss the motivation of using the GW-BSE method. Firstly, the BSE framework has been applied to predict the optical properties of bulk solids. Secondly, the electron hole attraction has the correct asymptotic behavior to describe the charge transfer excitations in molecules. Thirdly, the GW approach is known to give the correct HOMO-LUMO graph for a variety of organic systems. For example, in figure 2, we compared the GW HOMO-LUMO gap versus the CCSD HOMO-LUMO gap. Here, CCSD stands for coupled cluster with single and double substitutions. We see that the gap for the GW PBE represented by the solid red triangles, is largely underestimated, whereas for the GW Hartree fog, it is slightly overestimated, which is represented by the solid yellow circle. In this respect, the single shot GW Hartree fog is a good starting point compared to the pure density functionals. In this slide, we are going to compare the optical spectra and the singlet-triplet gap calculated by the TDDFT and the GW BSE method. Note, all the methods are listed in the first column of the table. The equilibrium geometry of the PhCz molecule is optimized at the DFT level with the B3 lip and 631G basis. This is also shown in figure 1. We use Gaussian 16 for all DFT and TDDFT calculations and the excitation package for the GW BSE calculations. The PhCz is a relatively small molecule with only 32 atoms. This allows us to compare the TDDFT and the GW BSE method efficiently to understand all the systematic differences between the methods. Next, we focus on the first singlet excited state energies with dominant HOMO to LUMO transitions. This is given in the third column of the table. For MO6, we see that the S1 is 4.46. For LC omega PBE, the first singlet excited state energy is 4.23, and the corresponding singlet excited state energy for GW BSE method is 4.42. We further plot the optical spectra for all these methods and try to compare them. In the top panel, we see the MO6 2x optical spectra. In the middle panel, we see the optical spectra produced by LC omega PBE, and the last panel corresponds to the BSE results. We see the peak positions are very well matched across all the methods. Thus, we believe that GW BSE is in good agreement with MO6 in terms of the singlets. Next, we focus our attention to the triplet excited state energies with dominant HOMO to LUMO transition. Here we see that for MO6, the first triplet state has an energy of 3.74. For LC PBE, the first triplet has an energy which is 3.46, but a good HOMO to LUMO transition. However, for the triplets, we immediately see that state T3 has a HOMO to LUMO transition of 58%, but not the state T1. This means the lower triplet states suffer from an instability problem in the GW BSE method. However, to effectively compare the singlet triplet gap, we should compare the wave functions across the methods. For instance, if we subtract the energies for the first singlet and the first triplet for the MO6, we see that the resulting singlet triplet gap is 0.72 electron volts. Similarly, for LC omega PBE, it is 0.77. However, for GW BSE method, we should subtract S1 and T3 because they correspond to the HOMO to LUMO transition, which gives a value of 0.76. This matches very well with the experiment as well, which shows a value of 0.55. However, other theoretical results suggest that the singlet triplet gap lies somewhere between 0.55 and 0.8. Now we try to identify the local excited and charge transfer states for both the singlets and triplets. Thus, we plot the charge transfer length for the first 16 excited states for the singlets, which is shown in figure 1, and for the triplets, which is shown in figure 2. The charge transfer length is defined by the following expression, where Ki to A is the configuration coefficient from the molecular orbital I to the virtual orbital A. Note, here the states with charge transfer character means that the electron and holes are localized on the donor and acceptor fragments of the molecule, whereas the local excited character means they are localized on either the donor or the acceptor fragments of the molecule. However, any state that shows a delta R of greater than 2 angstrom can be regarded as a charge transfer state. Thus, for the singlets shown in figure 1a, we identify the states 1 and 3 as the local excited states, and they are marked with solid blue, and state 2, 4 and 15 are marked as charge transfer states, which are marked with solid green. Similarly, for the triplets, we identify the local excited states as T1 and T2 marked with solid blue, and states T3 and T15 are the charge transfer states which are marked with solid green. Now to further analyze the nature of the identified CT and LE states, we plot the charge transfer spectrum and the interfragment charge transfer heat map. The interfragment charge transfer heat map is basically used to study the amount of charge transfer between the different fragments. Thus, we divide the molecule into two distinct fragments, which is fragment 1, which corresponds to the donor, and fragment 2, which corresponds to the acceptor part of the molecule. Now, the charge transfer spectrum is given in the bottom left panel. The solid black line corresponds to the overall UV spectrum, and the solid red line corresponds to the interfragment charge transfer from 1 to 2, and the blue line corresponds to the charge transfer from fragment 2 to 1. Note the peaks are already identified for the corresponding states, and the corresponding heat map for S2 is given, which is a charge transfer state. In the heat map, the electron, the hole, and the overlap functions are given as a function of the fragment 1 and 2. As we already discussed, for charge transfer state, the localization of the electron and hole should be on the different part of the fragments, and we can see that clearly in state 2. And for state 1, we see that the electron and hole are localized on the same part of the fragment, thus the overlap is very high. Through this, we can clearly identify the CT and the singlet excited states. Using the same analogy, we can also identify the local excited and charge transfer states in the triplets as well. Here in the bottom left panel, we plot the charge transfer length as a function of the total number of states for the triplets, and we have already identified as the state 1 as the local excited state and state 15 as a charge transfer state. Now if we look at the corresponding heat map, we see that for the T1 state, the electron and hole are both localized on fragment 1, and thus the overlap function is extremely high. It is similar to T2, which is also a local excited state. However, state 15, we see that the localizations of electron and hole are on the different part of the fragment. For example, the hole is localized on fragment 1, whereas the electron is localized on fragment 2. Thus, the overlap function is extremely low, and we can identify them as a charge transfer state. We go one step ahead and plot the electron and hole distribution map for the local excited and the charge transfer states for both the singlets and triplets. Here in the top row, we can see that the charge transfer states are clearly identified, where the electron and hole clouds are localized on different part of the fragments, and same is with T15, which is given in the bottom part of the panel, whereas for the local excited states, the electron and hole cloud are localized on the same part of the fragment. I would like to end my talk with some important conclusions. For example, the GW Hartree-Fock is a good starting point for gas phase calculation of the singlets. The triplet BSE energies are lower because they suffer from the triplet instability problem. However, the singlet-triplet gap can be compared by tracking the wave functions of the states corresponding to the TDDFT. The CT excited states and their character can be very well identified with the fragment analysis and the heat maps. The theoretical analysis provide a roadmap for the future analysis of CT geometry relaxations and other set of TADF molecules with low singlet-triplet gaps. Thank you.